Today in this video lecture, we will see numerical 1 on topic member subjected to normal stresses in two mutually perpendicular directions, accompanying by a simple shear stress. Numerically, figure 1 shows an element of a structure subjected to sigma x. Stress in x direction is 300 MPa and shear stress is 150 MPa. And to calculate change in length of diagonal, if Young's modulus is 200 GPa and Poisson's ratio is 0.3. First write given data. Sigma x is 300 MPa. Normal stresses in two mutually perpendicular directions, sigma x and sigma y, but here sigma y is 0. They don't tell us about sigma y in numericals, so let us consider sigma y is 0 MPa and tau shear stress is 150 MPa. Here sign convention for shear stresses. See, sign convention for shear stresses. If shear stress acts like this, anti-clockwise direction, then it is negative shear stress. If shear stress acts like clockwise direction, then consider it as a positive shear stress. See, in our numerical, shear stress is this, and this is anti-clockwise. So this is minus 150 MPa. This E is 200 GPa. E is Young's modulus or modulus of elasticity. And this E is nothing but the ratio of the stress to the corresponding strain is a constant, and this ratio is known as modulus of elasticity or Young's modulus. That means this E is equal to linear stress upon linear strain. E is equal to sigma upon E, and unit is Newton per mm square. Convert this gigapascal into megapascal. 200 into 10 raised to 3 MPa. From GPa to MPa, multiply it by 10 raised to 3. And in numerical, they also given us mu. Mu is Poisson's ratio. Poisson's ratio is nothing but see definition of Poisson's ratio. When the homogeneous material is loaded within its elastic limit, the ratio of the lateral strain to the linear strain is constant and is known as Poisson's ratio. Poisson's ratio is denoted as mu. That means lateral strain divided by linear strain. and material is homogeneous material and within its elastic limit. Okay, and to find change in length of this diagonal, change in length, that means delta L. So in numerical they have given us stress in x direction 300 MPa, stress in y direction is 0 MPa, shear stress is 150 MPa, this is negative, and Young's modulus is 200 into 10 raised to 3 MPa and Poisson's ratio is 0.3. So first calculate normal stress. Methodology of solving this numerical is first calculate normal stress, then tangential stress, then strain, then change in length. So normal stress. Formula for normal stress is sigma n is equal to sigma x plus sigma y upon 2 plus sigma x minus sigma y upon 2 cos of 2 theta plus tau sine of 2 theta. Here sigma x is 300, sigma y 0, tau minus 150. And theta is 30 degree. Here theta is 30 degree. That means this angle is also 30 degree. And this theta is nothing but the 90 minus 30 degree. 90 degree minus 30 degree. That means it is 60 degree. (300 plus 0 divided by 2 plus 300 minus 0 divided by 2 cos of 2 into 60 plus tau is minus 150 into sine of 2 into 60, that means 120 degree. Therefore this sigma n comes 300 divided by 2 plus 300 divided by 2 cos of 2 into 60 degree plus in bracket minus 150 into sine of 2 into 60 degree is minus 55 Newton per mm square. This is normal stress. Second, tangential stress. Sigma t is equal to sigma x minus sigma y upon 2 into sine of 2 theta minus tau cos of 2 theta. Therefore sigma t is equal to sigma x is 300 minus 0 upon 2 sine of 2 into 60 degree minus tau cos of 2 theta minus minus 1 of 50 cos of 2 into 60 degree. This is tangential stress is 54.9 mm square. Newton per mm square. Sigma n and sigma t are the traces acting normal and along to the diagonal. Next, calculate strain. Strain along the diagonal. Formula is E is equal to sigma t upon E minus mu into sigma n upon E. Sigma n is minus 55 and sigma t is plus 54.9. E is 200 into 10 raised to 3 minus mu is 0.3. Sigma n is minus 55. So this strain along the diagonal is 3.57 into 10 raised to minus 4. And strain have no unit. And our objective is to find change in length of this diagonal. So strain along the diagonal formula is strain along the diagonal is nothing but the change in length of diagonal upon original length of diagonal. That means this strain is equal to this change in length upon original length. Consider this as equation 1, and this for this C we don't know this original length of diagonal. We know only this side of diagonal, side of this rectangle, this 25 mm, and we need to calculate this diagonal. So by using this angle sin theta is equal to opposite side upon hypotenuse, we will get this diagonal length. So sine 30 degree is equal to 25 upon, consider, let us assume this as L. Sine 30 degree is equal to 25 upon L. Because our objective is to calculate this delta L, we know this E, we don't know this L. So we need to calculate this L, and after we get this L, we will calculate delta L. Now sine 30 degree is equal to, opposite side is 25 mm and divided by L. Therefore this L is sine 25 upon sine 30 degree. That means this is 50 mm. Length of diagonal is 50 mm. Now equation 1 becomes E is equal to delta L upon L. E is 3.57 into 10 raised to minus 4. Delta L is as it is, and L is 50 mm. So this delta L is equal to 3.57 into 10 raised to minus 4 multiplied by 50. It is 0.01785 mm. This is change in length of this diagonal. For stress acting C, with the help of stress acting on x direction 300 mm, shear stress minus 150 MPa, Young's modulus and Poisson's ratio, we calculate normal stress minus 55 Newton per mm square, tangential stress 54.9 Newton per mm square along the diagonal, and strain is strain along the diagonal is 3.57 into 10 raised to minus 4, and change in length is 0.01785 mm. So this way our numerical completes. Thank you very much.